Hi everyone, this is a video to go back over chemotaxis since we ran out of time to finish it in class. As a reminder, the MCP is the methyl accepting chemotaxis protein. This is a protein in the cell membrane that will bind either attractants. So these are going to be things that the bacterium would like to move towards in order to consume, things like sugars and amino acids. Since these are delicious and nutritious things for the bacterium, if attractants are bound, then the cell will enter a run, which is a counterclockwise rotation of the flagellum, and essentially makes the cell go in a forward direction. This is the normal position for the flagellum. The MCP can also bind repellents. So these are, I think that's a name. Repellents are toxic things or compounds that may be warning signals for the cell. So repellents include metal ions, like heavy metal ions, or fatty acids. Because some fatty acids are antibacterial, other fatty acids are warning signals. And so if the MCP binds a metal ion or a fatty acid, the cell wants to move away from that spot as soon as possible. And so if a repellent is bound, then the cell will enter a tumble, which is a clockwise rotation of the flagellum. And you will remember that the tumble simply stops the cell from going in the direction that it was going and repositions the cell to a new random direction. The tumble does not have a lot of control over which way the cell goes. If nothing is bound, if the MCP is empty, well, that's no good either because the cell has nothing to eat right then, and so the cell will still enter the tumble. If the MCP is empty, the cell is hoping with air quotes, to move into a new random direction where there will be food. Okay, scooch this up a little bit. So we are going to use, too far. We're going to use green for the run, green for go. And so if the MCP is bound with an attractant, so we're going to just say bound, but when we say bound, we mean bound with an attractant. If MCP is bound with an attractant, then we do not get Ki-A autophosphorylation. And that autophosphorylation normally uses ATP. So we do not get Ki-A autophosphorylation. Because we do not get Ki-A autophosphorylation, we also are unable to make the Ki-Y phosphate. And so the Ki-Y phosphate, if it were present, would bind to the switch proteins, Fle, M, and N. But since there is no Ki-Y phosphate, then the switch proteins, Fle, M, and N, remain unswitched, remain unbound, I'll say, and, oopsie, remained unbound and unswitched. And so the cell continues in the normal counterclockwise rotation of the flagellum, which gives the run. Okay, so this is great, except that if the cell is always able to respond to a flat level of presence of attractant, then the cell will have no way to tell where there's more attractant, right? And so the cell might be stuck on the periphery of where it first encounters the attractant, but is unable to detect which direction the source of the attractant is if the cell always stays in the run if MCP is bound. So the cell needs a way, when attractant is present, to make the MCP less sensitive to that attractant. This will allow the MCP to only detect increasingly higher levels of the attractant, so then the cell will move toward the higher levels of attractant instead of just staying where there's some attractant. So where the MCP, or really any different receptor protein, becomes used to the levels of the thing that it's binding, that is called adaptation or habituation. And so adaptation or habituation prevents a response, prevents the ability to detect a higher level of the thing. So if the receptor is full at a low level, then the receptor can't get fuller, right? It's already full. And so adaptation or habituation prevents the cell from detecting a higher level of the attractant. And so the cell has to do something about this. And so what the cell does is there is a protein called KeyR. KeyR methylates MCP continuously. So everywhere that there is an MCP, there is a KeyR. KeyR does not need to be turned on. It is always working, and the job of KeyR is to methylate MCP. This is important because MCP methylated is less sensitive to the attractant. Okay, so if you have MCP methylated and there is a small level of attractant, the MCP will not bind the attractant because MCP methylated is less sensitive to low levels of the attractant, and so the low levels will not be bound, and so this process would not happen. It would be as if the receptor was empty. So again, the methylation allows the cell to be able to tell low level of attractant from high level of attractant by desensitizing the receptor to low levels of attractant. Hopefully this makes sense. So now I'm going to get rid of this page and we're going to talk about the tumble. Okay, so the tumble happens if the cell is bound to, not if the cell is bound, if the MCP is bound to a repellent or if the MCP is empty. We're just mostly talking about attractants, actually. That's the way that chemotaxis is typically presented, and repellents are just backwards what happens with attractants. So we are going to say, finding my spot on the page here. Okay, so red is for not go, right? So if the MCP is empty, then the cell needs to get out of there and get somewhere else. And so it is going to somehow activate the tumble. And so, oopsie, the empty MCP empty, does not prevent the autophosphorylation of the key Y. And so you get, of the key A. So you get key A autophosphorylated. Again, this uses ATP. The key A, which now has the phosphate group, leads us to phosphorylated key Y. This phosphorylated key Y will then bind to the switch proteins FLE-MNN and the bound switch proteins will reverse the direction of the flagellum, and so this gives a clockwise rotation, which gives a tumble motion to the cell. And again, the tumble motion is just a stop and a random reorientation. Okay. So, do you guys remember from like briefly ago when we have the methylated MCP, then that MCP is less sensitive to the attractant. So if we are in a tumble situation because the MCP is empty, how is the cell to be sure that there's really nothing to eat there and that it just can't detect if the attractant is really low? So that is where another protein comes in key B. So if the methyl accepting chemotaxis protein is empty, then we will get key A autophosphorylated. In addition to activating the tumble, the autophosphorylated key A will give us a phosphorylated key B. The phosphorylated key B demethylates the methylated MCP, giving us MCP lacking the methyl groups, and restoring the sensitivity to low amounts of attractant. So it is both the run and tumble, which allows the cell to move toward the attractant or to randomly get into a different direction. And then the key Y, the key Y is involved in the switching. The key R keeps the cell from adapting to low levels of the attractant in order that the cell may be continuously seeking the highest possible level of attractant. But what if the cell has swum out of the attractant and it needs to be able to recognize a low level in order to get back to the source? So then, when the MCP is empty, we get the phosphorylated key A, which activates tumbling, but which also activates the phosphorylated key B. The phosphorylated key B counteracts key R. The phosphorylated key B demethylates and restores the sensitivity of MCP to low levels of attractant. So it's these 4 proteins, well really it's 3 because it's key A phosphorylated or not, and then key B phosphorylated and key R phosphorylated that determine both the sensitivity of the MCP and how likely the MCP is, or how likely the flagellum is to run or tumble. One thing that I remembered that I just forgot to tell you is that we also have key Z is present, and its job is to continually remove the phosphate group from key Y, turning key Y phosphorylated to key Y unphosphorylated. And so the job of key Z is to prevent the cell from being in a permanent tumble, because a permanent tumble makes it hard really to get anywhere, and the cell is unlikely to move toward food. And so the whole point of this is for the cell to be able to detect the attractant and to move toward the highest possible concentration of the attractant. And so there must be a way, once the tumble is activated, for it to be turned off, and key Z is involved in turning off the tumble by removing this phosphate, and then this key Y unphosphorylated can no longer bind to the switch, and then the run is restored. So hopefully that makes more sense. I'm sorry this was a little bit on the long side.